So at a high level, if we can actually view the CPU in an event model as follows. So the CPU is essentially a machine. It continuously fetches instructions, it executes the instructions, and then this typically goes on forever. But we can also view the CPU as follows, that after it executes a particular instruction, it checks if an event has occurred. So if no event has occurred, then it continues, it fetches the next instruction, and this cycle continues to go on. However, if an event has occurred, then the processor, the hardware itself would suspend the current task, save certain registers uh, uh, corresponding to that task, and then force a specific event handler to execute, right? So after the event handler completes its execution, it returns and the CPU continues its execution as follows. So put another way, so typically the CPU would fetch instructions, execute it, and this cycle goes on. But if there is an event that occurs, it halts or suspends whatever it was doing, it executes the event handler, and then continues to do what it wants, right? So this part is essentially what is done by the OS, right? The suspending the current task and moving from the user mode to the supervisor mode is done automatically by the CPU, that is by the hardware. Okay. Now, in XV6, it's we have three modes. We've discussed this before. We have the user mode, the supervisor mode, and the machine mode. And the machine mode is the most privileged, while the user mode is the least privileged, right? Now we essentially have different interrupts for different modes, right? So machine mode could have its own interrupts, the supervisor mode could have its own interrupts, and so on. Now each of these interrupts could be enabled and disabled globally, right? Now now we have registers known as the status registers for each mode. So for example, we have the M status register for enabling and or disabling machine mode interrupts, right? So using the M status register, we have a bit, say MIE, which is here, which can be used to enable machine mode interrupts. So if this bit is set to 1, right, in the M status register, then we essentially can enable interrupts in machine mode. Similarly, there is another bit called SIE, right? So SIE essentially bits. The M status register has two more entries. One is called the MPP, which has 2 bits, and the SPP, which has 1 bit. So these bits essentially hold the previous mode before the interrupt occurred. So what does this mean, right? So let us essentially go back over here and say that we were, let's say, executing in the machine mode. Say that the RISC-V has the machine mode, it has the supervisor mode, and it has the user mode. Okay. Now, when an interrupt occurred in RISC-V, this interrupt can be configured to be a supervisor mode interrupt or a machine mode interrupt, right? So what this means is that depending on what interrupt occurred, the uh, the CPU core could switch to the supervisor mode or the machine mode, right? So in this case, we have taken that from user mode, it switches to the supervisor mode. Another case that can occur is the following, right? Now we have the supervisor mode executing, right? And during the point where the supervisor mode is executing, we have an event that occurs, okay? And this event causes the event handler to execute, right? So notice the difference over here. So here there's a switch from user mode to supervisor mode, right? On the other hand, if the CPU core was already in the supervisor mode, there is no switch, but the event is still serviced, right? So here we see that uh, there is no shift in mode, apparent shift in mode, but we have the event getting serviced by some particular function. Okay, so after in each of these cases, when the event has completed service, we need to switch to the correct mode, right? So for example, over here it was in user mode, it switched to supervisor mode. So after the event is serviced, it should go back to the user mode, right? In this case, the supervisor mode, some say in the OS, some function has been executing. We receive an interrupt, it causes the event handler to be executed, and then we need to go back and continue our task. So in such a case, we still need to remain in the supervisor mode, right? Let us see an example in each of the case, right? So let's say we have a user process executing, right? And at some point there is a keyboard interrupt that occurred because somebody the user had pressed the keyboard. So this would switch to the supervisor mode. The kernel would execute. It would execute the keyboard device driver, and it would the um, read the key that was pressed, and at the end of it, it would essentially go back to the user mode, and the process should execute, right? So here I will just change the color. I will call this as the keyboard driver. So this was the user mode. The kernel ran in the supervisor mode, and we go back in the user mode. Okay. The other case is this, right? So we had, let's say, a user mode executing, and then this user mode made a system call, so it switched to the supervisor mode. The supervisor mode was executing the system call, and at this point we had the event, the keyboard interrupt that occurred. Okay, now this is also an event, right, and needs to be serviced immediately. So the CPU suspends what it was doing right now and goes and actually executes the keyboard device driver to read the contents, read the key that was pressed in the keyboard, right? So this over here is our keyboard driver execution. And naturally, after the keyboard driver executes and completes its execution, the CPU should continue from where it stopped and continue to execute this, and which was essentially the system call, and then go back to the user mode, right? So we see two different case scenarios, right? So while the keyboard driver and the functionality of the keyboard driver remains the same, what differs between the two is the fact that in one case there's an immediate switch back to user mode, while in the second case there is no switch to user mode. It continues to remain in the supervisor mode and continues to execute, right? Now these are the scenarios that we were actually specifying as user mode, supervisor mode, user mode, which is this case, and supervisor mode, supervisor mode, supervisor mode, which is the second case, right? Now to determine whether the CPU core should move to the user mode or remain in the supervisor mode is determined by the PP bit, right, or the previous mode bit. Yeah, previous mode. So, in this very specific scenario, we have the bit SPP, which is 1 bit, which is present over here, which essentially tells you what was the previous mode uh, for uh, um, for the processor's operation, right. So, if the previous mode was the user mode, the SPP bit would be set appropriately, so that when the keyboard driver completes, the CPU knows that the previous mode was user mode and therefore transitions to the user mode, right. Similarly, in this case, the previous mode was essentially the supervisor mode. Therefore, after the keyboard driver completes, it would continue to execute in the supervisor mode. Okay, so right, so the previous mode could either be the uh, supervisor mode or the user mode. Similarly, we have MPP, which corresponds to the previous mode when the interrupt occurred or the event occurred when the processor was executing in machine mode, right. So, for instance, you are actually executing in machine mode and then an event occurred. The MPP bits tells you what was the previous mode, right. So, notice here that MPP has 2 bits while SPP has 1 bit, right. Now, this is because when in machine mode an event can occur, or rather uh, an, a machine mode interrupt can occur either in the user mode, supervisor mode, or in machine mode, right. So, there are 3 ways, 3 previous modes possible for a machine mode interrupt, and therefore, this is encoded using 2 bits. However, for SPP, it interrupts could the previous mode could be either the user mode or the supervisor mode. Just so there's just 1 bit sufficient to encode that. Two um, other registers which are important for us is the aspect of interrupt pending and the interrupt enable registers, right. So, each of machine board and the supervisor mode have their own set of interrupt pending and interrupt enable registers, right. So, so here MIP stands for machine mode interrupt pending, and yeah, that's given by this. So, these two MIP is this. Now, two bits within this particular register which is important for us is the SSIP and the MSIP, the supervisor software interrupt pending, which is essentially this bit over here, and the MSIP, which is this bit here. So, this essentially tells you that we have a machine mode, we have an interrupt pending, a software interrupt pending in machine mode, or software interrupt pending in the supervisor mode, right. And besides MIP, we have another register known as MIE. So, MIE corresponds to machine mode interrupt enable. So, you can specifically enable or disable interrupts by manipulating this particular register. So, you have supervisor software interrupt enable, which is SSIE, which is this, and MSIE is machine mode software interrupt enable, which is this one, right. Now, these are so what are we able to do with these things, right. So, we are able to, in machine mode and in supervisor mode, we can enable software interrupts or disable software interrupts. That's with the interrupt, the MIE, the interrupt enable register. At the same time, we can also identify whether a software interrupt has occurred in machine mode or in supervisor mode by the SSIP and the MSIP bits, right. Now, very similar to this, we have timer interrupt pending and the timer interrupt enable bits. So, that is these parts over here. These correspond essentially to timer. So, we can essentially enable timer in machine mode or enable timer interrupts in machine mode or disable them. In supervisor mode, we can enable or disable timer interrupts and identify whether a timer interrupt is pending. So, STIP is this, MTIP is here, and the corresponding ones are here as well, right, interrupt enable. So, these are essentially important for us because when we are actually doing working in a multitasking environment, we would rely on the timer interrupt, enabling the timer interrupt and to context switch between different processes, right. Finally, we also have 4 more bits corresponding to enabling external interrupts. These are like hardware interrupts in machine mode, supervisor mode, and also identifying if there is any interrupt that is pending, right, either in machine mode or in the supervisor mode, right. So, at a high level, what this means is that with the help of these registers, the interrupt pending and the interrupt enable register, the programmer or in the OS in this particular case would be able to enable very specific interrupts such as software interrupts or hardware interrupts or timer interrupts, or also identify if any of these interrupts are pending or not pending, right, which of these interrupts are not pending. This way we will be able to identify what is the cause of an interrupt. Okay. So, now let us say we have say the interrupts enabled and we are essentially executing, right, and so we were running in user mode in this example. An event occurred, right, and we have switched, the hardware is essentially switched to the supervisor mode. Now, what we discussed here at this particular point is 2 things. So, we now know, we are able to identify what is the cause of the interrupt. So, we are able to identify whether it is a software interrupt or or what interrupt is essentially pending, right. Now, the next step is to be able to service that interrupt, right. Servicing that interrupt means that we need to identify that, in this case, that it is the keyboard that has actually caused the interrupt and invoke the keyboard driver. Okay. Similarly, if it had been a system call, then we would need to know that the event was essentially due to a software interrupt and we would need to start to service that software interrupt. Okay. So, in order to do this, the RISC-V processor has another register known as the Stvec register. Okay. So, the Stvec essentially would contain a specific the Stvec register enables the supervisor mode, or rather the Stvec register enables the operating system to configure the service routine or the function that would need to be executed when a supervisor interrupt has occurred, right. So, this is a register. It has this particular format as we see over here, in which the base part of it, which would hold the PC address, and we have 2 bits over here, which essentially tells you the mode, right, whether it's direct or vectored and so on. The basic idea over here is that when a supervisor mode interrupt occurs, the Stvec contents, the base part of this Stvec contents is loaded into the program, into the PC, right. So, this would force the processor to start executing based on this Stvec address, and at that address one would essentially hold the service routine or the function which will essentially service that particular interrupt, right. So, at this particular location we would have a function which would then identify the cause of the interrupt, whether the interrupt was an exception or a hardware interrupt or due to a software interrupt, and call the appropriate and take the appropriate action. Okay, so we will see this in more detail. Okay, so let us consider the situation that we are executing a user process. Now, very quickly we will recollect that the user process comprises of its own virtual address space. So, we have user process 1, and within that user process 1 we have the trap frame and the trampoline, which is right at the top of the virtual address space, and at the lower addresses you have the user mode code, user space code. So, all of this is accessible from the user space or from the user mode, and this trampoline and trap frame are accessed from the supervisor mode. Okay. So, we are now assuming that we are executing in the user mode, and during that time an event occurred. Okay. So, the event so this event would switch the processor from the user mode into the supervisor mode, right. Now, this switch from user mode to supervisor mode is done automatically, right, by setting the appropriate mode bits. The question here is that where in this trampoline should the program counter start, should the instructions be executed. So, this is essentially set in the Stvec register, right. So, when the event occurred, while the processor switches from user mode to supervisor mode, it looks into the Stvec register and loads the contents of the Stvec register into the program counter. So, we have the supervisor mode, the processor going into the supervisor mode, and the function or the instructions corresponding to the Stvec going to be executed, right. So, in our case, we have when this event occurs, we would have the function kernel vec that gets executed. So, the kernel vec is essentially present in the trampoline.s file in the x86 code. It is used to handle interrupts when in user address space. Okay. So, the reason this function user vec has executed is because the Stvec register contains the address of user vec. So, user vec now invokes the kernel vec, which is another function, and in this way the interrupts are essentially serviced, because and the OS would essentially continue, right. So, once we have moved into kernel vec, the next step is to identify what has caused the interrupt or what has caused the event, whether it is a hardware interrupt, or whether it's a system call, or whether it's an exception, right. So, this is the next step which is done, and it is done by looking into the scos register, right, into the this is done using the scos register, by the cos register which we have discussed. Okay. The complete flow for interrupts handled in x86 is as follows. So, we have the user process executing, and the event an event gets triggered. Now, this event would trigger the hardware to store the program counter into this EPC register. EPC register stands for exception program counter, right? And from here, it would either move to the user-vec function or the kernel-vec function, right? So this choice, whether it moves to user mode, user-vec or the kernel-vec, depends on the previous mode of operation. If the previous mode for the CPU before the event occurred was user mode, then the user-vec function would be executed, as we have discussed over here. So the Stvec would then contain the user-vec function's address and execute the user-vec function. On the other hand, if the kernel is already executing, for example, let's say it was performing a scheduler or it was doing executing a device driver, then the Stvec is configured so that it points to the kernel vec, right? So it would cause the kernel vec function to be executed, right? Consequently, the kernel vec would invoke kernel trap, while the user vec would invoke the user trap. So going back to this thing and highlighting what happens in each case is that if you are in user mode and event occurs, we go to the supervisor mode, and the first function to be executed is user vec, right? We know that this function is executed because the register Stvec would hold the address of user vec. In this case, we are already in the kernel mode, right? And then an interrupt occurred. So the function that gets first executed soon after the interrupt in this case would be kernel vec. Okay, so the kernel vec function executes because at this point, when soon after it has switched to the kernel mode, we set the Stvec to point to the kernel vec function. Okay, so in other words, if I just look at how the Stvec changes while the user mode is executing over here, the Stvec holds the address of user vec. When an event occurs and it switches to the kernel mode, Stvec is changed to point to the kernel vec. Now, if an interrupt occurs, it would cause the kernel vec to essentially execute, right? So, okay, does it make sense? Okay, so let's now dig a little bit deeper, and we'll see the code for each of this, right? We will essentially see what happens in user vec, kernel trap, and so on, right? But the thing that is essentially common among both of this is the fact that once in kernel trap or in user trap, we need to essentially identify what caused the interrupt. It's noted that the cause could be different. The set of possible causes could be different in each case, right? So when the CPU was in user mode, right, and then an event occurred, this is the path that it essentially takes. And the cause could be either an external hardware, like say the keyboard for instance. It could be a timer, like the timer interrupt essentially interrupt essentially occurring, or it could be a system call, or finally it could be an exception, right? Now, if it's an exception like a divide by zero, then you simply need to kill the process. On the other hand, if the processor was in supervisor mode and an event occurred, the event could be due to hardware, like the external keyboard. It could be to a timer, or it could be an exception, right, like the divide by zero. Now, in this case, we essentially panic, right? So in the sense that this is a problem. This is an exception that occurred while the kernel is executing, and there's no way we can essentially recover from this, and therefore we panic in the sense that we essentially halt the kernel and don't go further. Another thing to note over here is that while you are in the supervisor mode, we cannot essentially have a system call that can occur. So we won't have software interrupts that can occur in this case, right? So when the CPU was in the kernel mode, but if the CPU was in user mode, then software interrupts can also occur. Okay, fine, last one I'm going. Okay, so how do we essentially distinguish between these various modes, whether the interrupt occurred due to hardware, the timer, the software, or an exception? This is essentially obtained by reading from the SCOS register, right, or the supervisor COS register. Now recollect that the COS register essentially would hold some code. This code is essentially filled up by the processor, and it would essentially indicate the cause for that particular interrupt, whether it was hardware, whether it was a software interrupt, whether it's an exception, and so on. Okay, so for RISC-V, we have RISC-V essentially defines a table like this, which essentially defines various exception codes for the SCOS register. For example, if it is a system call, right, or for example, in that matter, that is an E call, which is done at the machine, which is essentially invoked from the user mode, then the COS register would have the value of 8, right, because 8 is essentially an environment call from user mode. Okay. On the other hand, if an external interrupt occurred, for example, let's say from a keyboard or something of that form, then the SCOS register would hold the value of 9. Okay, so the value of the COS register is essentially filled by the processor, automatically by the processor, and read by the operating system in order to identify what caused the interrupt and then take the appropriate action. So we'll take an example of what happens when a process invokes eCall, right? So let's right. So we have a user process, and it is executing, and it essentially executes eCall, right? But before executing eCall, it essentially sets the A7 register to an appropriate value. For example, it sets it to say 10, right? Correspond, and what we have seen before is that the A7 register essentially holds the system call number, and is used by the kernel to identify which system call was required. So invoking the eCall essentially would move the kernel, move the CPU to the supervisor mode, and cause so the CPU moves to supervisor mode, and invokes the uservec function. Right, so uservec function is present in the trap frame. Oh yeah, uservec function is essentially present in the trampoline. Okay, so the uservec function would now change the context from the user processes page tables. So recollect that user process has its own virtual address space. So the uservec function would essentially change the context from the user's virtual address space to that of the kernel's virtual address space. So I'll use another color to say that we are now in the kernel's virtual address space. and eventually cause the function user trap to execute. Right. So, the user trap function would now first of all, where is it? Yeah. The user trap function would first of all look into the scos register and identify that the cause for this event was essentially an e-call, right. The way it would identify this is that it would know that the scos register essentially has the value of what of would have the value to be equal to 8, indicating that the cause for the event was essentially a software was essentially an supervisor um, software interrupt, right. So, now that it has identified the cause, it can now start to service the interrupt by calling the syscall function. Okay, the syscall function now reads the value of A7, identifies that, hey, this is the 10th system call, or the system call number is 10, and therefore identifies what is the system call and then services it appropriately, right. So, the code for this can be seen over here in the user trap present in trap.c. We read the rcos register and check whether it's equal to 8, right. So, if it is equal to 8, we know that it is a system call. Okay. Now, we also do something over here, just a check to identify if the process that actually invoked this has essentially been killed, right, or it has been terminated already. In such a case, we don't need to service the system call. Okay. So, then we increment EPC by 4. Remember, EPC is the exception program counter. So, it points to the eCall register. So, here for instance, your EPC essentially points to the eCall register. So, incrementing by 4 essentially means it points to the next instruction following the eCall, and after the system call completes its execution, this EPC is going to be restored back into the program counter, permitting the instruction following the eCall to execute, right. And finally, since we know that the cause is 8, therefore we invoke syscall, right. Now, syscall, as we have seen this function before, would look into the A7 register, which is stored in the trap frame, and identify the cause of this particular system call, that is the system call number, and then invoke the appropriate function to handle the system call.